The books that I got this from are actually wrong about it. They have mistakes. And so that's one of the reasons we don't use it as a textbook. We did many, many years ago, but we used what was called the red edition as opposed to the blue edition. And it would be ancient. I'm not to be surprised if you could even find it on Amazon anymore. But there are a lot of mistakes in the book. We've corrected those so that it becomes operational. Also, there's a fundamental design problem with the architecture that in an intermediate class I would ask you to find. I'm not going to ask this class to find it. And there's some things, for example, I think the textbook, at least the older, or the newer one, I think, says something about it shares a fetch cycle between this and the SAP one, which it in fact does not, because most of the instructions that are simple instructions take 4 T states. And if you gave up 3 of the T states to fetch, you wouldn't have enough T states to do the processes. So what it really does is it combines T2 and T3 together so that they become the T2 of this machine. But it's that sort of little mistake that's why I don't teach from the text on this one. And I've had people actually go find the textbook and then they answer questions on a test or something based on what's in the book as opposed to what we're really teaching you in this class. So just be aware of that.
So that's actually the heart of our question.
Oh, okay.
What is how could we accomplish, for example, add B in 1 T state, because we did find the book and it did say exactly that.
So I've been there before.
So essentially they just compress states 2 and 3.
Yeah, remember state 2 does count all by itself, right?
Right.
So the only thing you couldn't do was use the program counter during a state where you're updating it. Since we already used it in T1, there's no reason why T2 and T3 can't be collapsed into a single state.
Okay, so then
that leaves you 2 states to actually do the remainder of the addition, which you can easily do in 2 states.
Okay, yeah, that was 100% what our question was mostly going to be.
I must be reading minds today. That's excellent. Okay, well, I have 6 o'clock. I'm assuming everybody's here that's going to be here. So why don't we go ahead and get started? Did you all have any questions before we get started with the material for tonight? Okay, well, pull up the 2 documents I have here, the architecture, and have this handy. Hopefully you printed them out so you can look at them without having to clutter screen real estate. But I want to review for a second on the main diagram here the process of using the keypad. Make sure that we understand the protocols for that and that we could actually write code that will allow us to get data from the keypad. Once we've cleared the machine, the hexadecimal keypad is unlocked, meaning that you can push a key and the key will be moved into the input port. The acknowledge bit, which is sent from down here, is set to 0, so there's no acknowledgement in process or progress. The moment a person types a key, the first thing that happens is the keypad gets locked. Then the data from the key that was pressed gets put into port 1 here. Input port 1. And then finally, the ready bit is turned on. This is bit 01 in hex inside of this second port here, which is port 01. Once you've done that, eventually we're expecting sometime in the future, somebody wants to get that data. They're going to be looking into this port to see whether or not the key has been pressed or a key has been pressed. If it has, they can read 1 time from this input port. If they read 2 times, they'll get bad data, meaning that they'll get repeated data. But they can go here 1 time. They can extract a byte of data and put it somewhere, maybe the ALU, maybe the output register, wherever they want it to go. And remember, it's 8 bits, so it'll be in the right-hand 8 wires of the W bus. Then they're obligated to go down here and write to the acknowledge bit, which is 80 in hex. They're acknowledged to turn on that one bit. Now, when they turn it on, the port actually causes a pulse. It goes high and goes low again. So this acknowledge is seen by the keypad. When it sees a pulse, the first thing it does is it undoes the ready bit. And the second thing it does is it enables the keypad, which means the whole process could start again safely. Anybody have any questions about that process? Okay, let's write some code that will actually do that. Now, if we set up just the basic assembly program, we wouldn't normally have this statement, but we could org to 0. All that does is it tells the assembler, as you're generating code, make the next code appear as though it begins at 0 from this point. We don't need to do that because that's the default. We then do need to have a label. We'll call it, I don't know, we're going to pretend like we're getting keys, so let's call it the key. It's probably a loop since we're going to look multiple times. Call it key loop, or even key loop 1, something like that. Actually, we're not going to do anything fancy. Let's call it key loop so we're consistent with code we'll see later. Now, at the very end of our program, we need to have an end statement which names the starting spot. On many systems, the value you put here will tell the program counter where to begin after a clear. However, on the machine we're running, doesn't matter what you put here, but it's going to start here. It'll always start at address 0, regardless of what you put here. So we're going to make those two values match. This statement is an assembler directive, meaning it doesn't generate any machine code. Rather, it just tells the assembler things about the assembly it's getting ready to do. Now, the first thing we said we need to do if we want to get something from the keypad is we need to check this register to see if the ready bit has come on. Now, does anybody have any ideas about an instruction that we could use in order to make that happen? Now, remember, in an assembler, you have to give it all the details. You can't do like you do in a higher level language and punt. You've actually got to give it the details on what you need to be doing. Robert, what do you think is a good first statement?
If we know the address for the register, could we do LDA, the address?
Well, remember, there's two different types of addresses. We have memory addresses, which is where data goes. We have 65,000 bytes of that, right? 65,536 bytes. We also have input addresses. They can only be addressed by two different types of instructions, the in instruction or the out instruction. Okay, so knowing that, do you have an idea? Scott, I saw you put your hand up there for a second. Do you have an idea of what we could do as a first instruction?
You could do in, and then I'm guessing the address of input port 2 is 1.
Okay, so we can do an input instruction at address 01. Now, what that will do is it will take the data that's in the port, make a copy of it into the accumulator. Now that doesn't tell us anything about what's there. It just made a copy we can now check. Remember, the value that's here may have other bits turned on either randomly, or if we had the serial feature, might have a bit that's changing asynchronously to the ready bit. So we can't count on having only copied the ready bit. We did copy it, but we've copied anything else that's in the register as well, which tells us that the next thing we're going to have to do has to check only that bit, not any other bit that's in the register. So we need an instruction that can do that. We're basically going to want to isolate that one bit. Anybody have any ideas? We know this from hardware, actually. We know how to block things. If I had this number right here, which is and I wanted to see if this bit right here was turned on, how would I do that? What operation would I use, and what would the mask look like? Scott, what do you think?
Yeah, the mask is kind of the clue here. You could do bitwise and with.
And what would the mask look like?
0001.
Well,
and then 0000.
right. And you said let's use an and, which is bitwise. Wouldn't it be nice if this machine had an instruction like and? Let's look at our instruction set. Well, here's an and. We can and B with the register, the accumulator. We can and C with the register. But here's one that's even nicer looking. We can and it with a byte, which could be our mask. And what's that going to do? That'll set a flag for us, won't it? Okay, let's think about that a second. If we were going to do that, an and immediate. What's the mask look like that we have to use? Well, we would have to have a mask that lines up with the data we're interested in. Now, this address happens to have the same value as the place where the ready bit is, but the ready bit is bit 1, right? So we should be able to do an and immediate of 01. This 01 is the mask of the position in the register. It's not the same 01 as this. This 01 is the register number. They happen to be the same. So once we've done that, that's going to set the flag. Is it going to set the 0 flag or the sign flag? Well, it can't set the sign flag because we've guaranteed the sign will be off because we put a 0 in that position. This bit will give us either a 0 or a not 0, depending on whether or not it's really on in the register. So what tests do we have to do here to test to see if it's on? What's going to happen if we get a 0? Scott, what's going to happen?
If we go
what
with,
does it mean?
if we go with
What
the,
does it mean?
if we go with the JZ here, if the 0 flag is on, then we're going to jump to whatever address we supply right after the JZ.
Well, does it mean we have a character or don't have a character if we get a 0?
Means we do not.
So we're going to go back and try again.
Yeah.
If we ever do get to the next line, we have a character. So where is the character? Robert, where is it?
It's in input port 1, waiting to be acknowledged.
Well, we have to get it out of the input port. So how do I get it out of port 00? There's only one instruction I can do it with.
Yeah, the in
And what port number is it?
00.
Where's it going to wind up?
It is going to wind up at the MAR, right?
Nope. Where's the input instruction always put its data? Scott?
The accumulator.
Okay, so it's in the accumulator. Now we want to print it out. So how can I get it to the output register? Robert, what do you think?
We have out, but that's out byte.
Well, we want to put a byte out. We're trying to put the character that was just read in. Where we're going to put it? What's the number of the output port that has the hexadecimal to display?
Oh, 00.
Which one's the one that has the hexadecimal display?
Oh, port 3
Which is coded how?
has 11 or
Which is
no,
coded
sorry,
how?
03.
Oh, 02. Remember, they're all
02. Right. Sorry.
Okay, now that we output it, we now have to acknowledge it. How am I going to acknowledge it? Well, we know ultimately there's going to be something that's going to put something in the accumulator that we need to output the register 03. What is it we're going to put in the accumulator? And how do we get it there? What's it say we got to write down here? The acknowledged bit is the 7th bit, so that's 80 is the number we have to write in hex. How do we get that in just whatever? This guy's going to take his value from the accumulator, so we got to get an 80 into the accumulator. How can we do that? Scott?
MVIA with the...
Well, it's going to be moved to the accumulator.
And the byte would be 80.
You got it. At which point we move it to the acknowledge bit. Now let's say we wanted to go back and do it again. We would just do an unconditional jump to key loop. Now that follows our protocol to the letter. Check the second input port by ANDing it with a 1 to see whether or not it is a 0. If it's a 0, we don't have a character. If we ANDed and we got a 1, that means that bit was on. Then we can go ahead and get the character out of the first port, write it to the display, then we can load our acknowledgement bit and acknowledge it. Then go back to key loop, do it all again. Give me a green circle if that sort of makes sense, and a red circle if you feel like you've been to the dentist. Yeah, I thought so. Okay. Let's go through the process and think about it. In this particular assembler, a semicolon starts a comment and goes to the end of the line. So what are we doing here? We're getting the data in input, let's just call it in port 2. We're isolating the ready bit. If we now have a 0, we try again. We don't, we have the data. But the data is in the other register, so we get the data. We could do something else with it, but in this particular case, we just output it to the lights. And we set up the acknowledge bit. We output it to the acknowledgement register and do it again. So it's a very simple little dance. We have to get all the steps right, but it's a very simple set of things that happen. The reason we have to isolate the ready bit and look at it is if we, for example, didn't check the ready bit and we just went to the register, we'll read whatever's in the register. If we check it once and we don't acknowledge it, it'll still be on the next time we look in this register, and we'll go get it again thinking they've been repeating a key, which they not necessarily have been. So we have to follow this protocol in order to be able to read out and get the character isolated. And then we need to acknowledge it when we're done so that the thing can reset and be ready for the person to type another key. Scott, why don't you explain that to me?
Sorry, explain the program we just
explain the program.
So we're basically setting up a loop that when valid data is entered on the keyboard, it will basically be printed out to the LED lights in our output. It's just basically echoing what we type in.
Okay, now explain the protocol. Okay, I'll just throw it out as a general question. Who knows what happens when we hit clear? What's the state of the keypad? Second?
The program counter is set to all zeros.
Yeah, what's going on with the keypad? Well, as soon as we hit clear, what happens to the keypad? Scott?
I'm just guessing that it'll be unlocked.
Right, it's unlocked and what?
Um, the acknowledge bit is low.
Well, it doesn't control the acknowledge bit, but it is low.
It's not providing anything to the input port yet. That's all I got.
Well, we don't know that. We don't know for sure, but it's not providing anything valid. Okay, there are two things that happen. The keypad is unlocked. The ready bit is turned off. And next time I ask that question, somebody should know the answer to that. I've said it about 5 times now. Somebody comes along and pushes a key. What's the state of the keypad and the input registers at this point? Mohammed?
Keypad will be locked and input register will take in that key, whatever we press in the form of nibble.
Okay, keypad is locked. The data from the keypad that was pressed is in input port 1. Ready is turned on. Now the keypad doesn't care at all whether you read the key or not. If you never read it, but you acknowledged it, it would just reset itself and you'd lose the character. So we're obligated, if we want to follow the entire protocol, to read out the data once we notice this is ready. We want to read the data somewhere, and we're going to load it into the accumulator in order to get it out of that register. Once we have it, we can put it somewhere else if we want to. In our case, we put it in the output port 3. But then we're obligated, before we read it again, to set the acknowledge bit on in the output port. The output port doesn't care that we turned it on. It just gives a pulse when it sees us turn it on, which this guy sees, which tells him to turn it not ready and then unlock himself. And that's the protocol that this code pays attention to. Now, it's key that you understand what's going on right here. In assembly language, that happens a lot. In higher level languages, they go, oh, well, they just don't know what's going on. I'll take care of it for them. Here, you have to specifically say what you're going to do. Our goal here is to take the data we've read in and isolate the one bit on the right. Ands can only be ones if the bits on both sides, the A and B, are both a 1. So the only bit that could ever be a 1, if we use this as one of the numbers, is the rightmost bit. Since that's the one we're interested in, if it's a 1, it means it was turned on in the register. If it's a 0, it means it was still turned off in the register. So we can check to see whether or not the register was all zeros, meaning that it was a 0 when we did the AND. Go back and try again. Or if it turned out it's not 0, it'll fall through and we can go get the data. So we want to make sure we really understand that sequence of things. Okay, now let's try to do this using an emulator. See how we do. I'm going to keep these two guys around in case we need to talk about them. By the way, one of the things that was important when we did the AND was to look over here and make sure it really did set the flags. If we'd done something like a move, it doesn't set the flag, so we couldn't have used it to isolate any bits. Okay, we want to go get to this file. Do that, give me a green circle when you have it. And unzip it somewhere on your desktop. Okay, now when you get it, let's see what I do there. I think I just dropped my whole folder on that. This guy. When you get the folder, if you open it up, you'll see a SAP2 simulator directory. Go into that, and you'll see some files. Now you're going to need your console, so go get your DOS prompt. And then what we want to do is we want to CD until we're in that particular directory that has these files. So I'm going to do Malby in a different place than you, but it'll be the same sort of notion. So I'll CD I have to go to desktop first. Then I can go to SAP2 Sim. Oops. I think it's SAP2 Sim. Oh, no, I can't go to desktop. I have to go to OneDrive on this machine. No, it's SAP2 IDE. Then I go to the SAP2 Sim directory. So let me know when you got your command prompt in that particular place. If you don't have it, give me a red circle. Robert, what trouble are you having?
Same issue you were having. I just got to get to the OneDrive side of things. Taking me
Okay.
a sec.
Patricia, you having a problem?
I'm just trying to direct it yet.
Okay. Matthew, you having a problem?
I just had to get to the OneDrive first before,
Okay.
and
Yeah, I keep forgetting I have one machine that has it and another machine that doesn't have it. And I always go to the wrong one.
I just have to be in the folder. I don't have to be. Okay, I see. Yep.
Right, right. Same folder I'm in. Okay, now if you're on Windows, you're going to be able to use the batch files that are in here. If you're not on Windows, You look inside the batch file, there is a Java command which you can enter like on Windows or Linux, not Windows, on Mac OS or on Linux. Where this funny looking thing at the end is where you put the name of the assembly file you're going to be assembling or the hex file you're going to be running. So you would just use the contents of the file. We as Windows gurus, however, will just use the assembly files. Now in here, if we look at it again, let me give you a tour. There's the assembly batch file. This runs the assembler. It takes in a file ending in ASM, and it produces a file ending in HEX, hex. This is a sample program we're going to look at in a second, and this is some sample output. You may not have both those files right now. You might not. These two jar files contain the assembler and the simulator. Simulator is run with the sim batch file, and that's really all you have to know about right now. So let's look at the sap2.asm file in Notepad, or whatever your favorite text editor is. And you should find something striking about the code that's in there. If you were paying attention the last 10 minutes, we just wrote this code. How did it magically get in that file? Ooh, ghosts. This close to Halloween. Well, no, I put it in there. And it's basically just a way to test out the keypads. I put a comment there just so you could remember what comments look like. Don't fill it up with a lot of comments because then you tend to write what the comments say instead of what the program does. Assembly is very clear. It only does what you told it to do, not what your comment says. So when I say that this is in from that port, that's all it does. It doesn't do anything like test a keypad. It just simply gets this into that. This ANDs this number with what's in the accumulator, produces a result, which as a result isolates the bit. But you don't want to type all that. You can just look at it and tell. So what we want to do is we want to assemble that. To do that, you just say ASM space, then the full name of the file, which was sap2.asm. You do that, and it comes back and it doesn't give you any bad messages. Doesn't mean the code is good. It just means that it assembled okay. Now, I'm going to make a mistake. I'll put a colon or something at the end of one of these lines here. I'm going to save it. Reassemble it. Notice I got an error, and it actually was nice enough to tell me it was on line 4. You'll be very lucky if it tells you very much about the error. This was a good error because I can count down to the 4th line and, oh, there's a colon there. It's got to go. They won't always be that clear of errors. This is not designed to be used by amateurs. It's designed to be used by professionals. And so it's assuming you know how to program. And so you don't need the extra special errors. Sometimes they would be handy, but the assembler just simply doesn't give them to you. Now, once it has run, it's going to produce a file, and you can notepad this as well, named after our file, like sap2.hex. So open that file up. Your favorite text editor will do it. I'm going to go over this part one time, not twice, so make sure you pay attention to it. Each line starts with a colon. This is a very common industry format for formatting binary loadable files for field programmable gate arrays, for ASICs, and for microprocessors, particularly for ROM-based microprocessors, or those that need this loaded in RAM or flash, and it's called the Intel format. Intel invented it. The next two nibbles are the length of the data. So we could go right down here and separate out the next two nibbles. What do I do here? So it says there's going to be 2 bytes of program in this line. 2 bytes, 3 bytes, 2 bytes, 2 bytes, 2 bytes, 2 bytes, 3 bytes, no bytes. The next 4 nibbles are the big end-to-end version of the address at which those bytes are going to be loaded. So this is the line says there's going to be 3 bytes of data loaded at address 4. The next 2 nibbles tell us what type of record we're looking at. 0 means it's one that's going to load data. 01 means it's a terminating record. Next, we have this many bytes of data. There's no bytes here. Now let's go just line up the last 2 digits. So if we have one of these files, we can work backwards to what the program had to be. For example, without looking over here, we should be able to take DB01 and turn it into N01. We also know it's at address 0 in memory and address 1. 0 and address 1. Here's address 2 coming up, so this is at address 2 and address 3. So we should be able to take this, even if we don't have the source code, and reverse engineer it from the source code back to the, or from the hex code back to the original code. If you want to be a quality hacker, you got to know how to do this. And, you know, I use the name jokingly because there are no quality hackers. So how do we find out what this means? Well, DB, we look it up on the address sheet. Remember the sheet we had that somehow reflects all these? What are we looking for? DB. Where is DB? Here it is. It's in from some register. What is? Okay, what's this guy? E6? E6, we go down the list. Here's an E6. It's an AND with some byte of data. What's the byte of data? It's an 01. So we could use this and that to derive the original program from this. We also could derive this just from looking at this code in memory. We could reverse engineer straight from memory to a hex file and then take the hex file and go back to the original source. Very handy to be able to do that, particularly when you've lost the original source code. The last statement is simply a terminator. It has no data, so it just uses the address 0. We then finally have this last byte. The last byte is derived from adding up all the other bytes and taking their 2's complement. So how would we do that? We would, if we were doing that down here, we take a 2. Of course, we're adding all the zeros as well. Plus a DB, which would give us DD. Plus 1 would give us DE. D. E. Take the 2's complement. We get a 2, 2, which we encode there. It's used by the hardware that loads this program onto the device to come back and recalculate it and determine that it loaded it correctly. If it can read back what it wrote and it matches this code, then it's a pretty good chance that the data was written correctly. This is called a CRC code, but we're not using it as that. We're just using it as, well, actually, this is not a CRC code. I'm lying to you there. This is actually just simply called a checksum. CRC code is a form of that. This is not one. So the checksum. Okay, now that we have this, if we had an SAP2, we could load it onto it and run it. Well, we don't have an SAP2 hardware chip, or nor do we have a programmer, but we have an emulator. So what we can say down here is we can say SIM stands for simulator, SIM space SAP2.hex. Make sure you say .hex. When you do, you're going to get a keypad come up and you're going to get a printout of what's running. Remember, we're in a loop, so it's going to run forever. But we should be able to click a key. I'm going to click the 6 key here. And when I do, the number 6 should appear down here in the LEDs. Pick an F should appear. Pick a 5 should appear. So we should be able to simulate the program we wrote using this simulator, and it should do exactly what we told it to do because it's aware of all the instructions. Give me a green circle if you got that to work. And everybody can get that to work because it doesn't rely on batch files. You can use the contents if you're on Linux or Mac. Okay, Peter, did you get it to work? Alka, did you get it to work? Okay, so I'm assuming everybody got that to work. Okay, I'm going to Control C, which will stop the program, and then I can type Y to get out of the batch program. Okay, so let's write a program. And then we can test and see that we understand how things are going to work. What we want to do is we want to take 2, and we wrote this the other night, 2 bytes of memory out of addresses 8000 and 8001, add them up, and output the answer. So I'm going to notepad a new program. Name it after yourself. I'm going to call mine drb1.asm. You can call yours after your 3 initials or 4 initials and .asm. Make sure it has .asm on the end. So I'm going to start. The first thing is I'm going to load the accumulator from address 8000. I'm going to move to the accumulator. I'm sorry, to the B register, whatever's in the accumulator. I'm going to load the accumulator from 8001. I'm going to add to the accumulator what is in the B register. I'm going to output the register 02, whatever's in the accumulator. I'll halt. I'll org 8000. Put a byte of 0 or a byte there. Let's put the number 32 in hex, and the second byte will be 17. I'm going to end and say start because that's where I'm going to end. I'm going to say that I didn't make any checking to see if I was making errors or if I had bad opcodes or whatever. I just wrote off my head what's there. So let's take our program and let's go over to our console window. We're going to say ASM, whatever your name of your program is. Mine's drb1.asm. Don't forget the .asm. Mine compiled okay. I must not have made any mistakes. Well, who knows? Logic might be wrong. Then I'm going to simulate drb1.hex. Now, if I just add this up in my head, I should have a 4-9. If I look up here, I have a 4-9. So I got the right answer. Notice this isn't running endlessly because we didn't loop. So we can look at this and I can explain to you how you use this for debugging. Give me a green circle if you got that code to work. Hey, Mikhail, what problem are you having?
I inputted the wrong thing, so the command prompt doesn't recognize the command I'm trying to run.
Okay. Well, you can fix that. That should be fixable. Do a Control-C if it's stuck in a command, and then you can delete the file if it's wrong and just create a different one. Okay, so let's look at what's here. Every time we have a new instruction, the 4 digits on the left address the memory where that instruction lives. This is the opcode of the instruction. That's all it is. So we could look it up to see what the opcode we're currently executing is. This looks like a load accumulator, the 3A. I recall D3 as an output. Well, I can look over here too to tell. Notice that the last instruction, the 7-6, doesn't show. Any idea why? Dante?
I imagine because it's a halt instruction, once it sees it, it just cuts off and stops bothering.
That's exactly right. Very good answer. It's just like the SAP1. It never gets to the execution phase, so the simulator never executes it. By the time it gets there, the clock is stopped. Robert, what's going on with you?
So actually had a question on that because our list here says that it takes 5 T states for a halt to happen. So I was hoping we could talk about why that is.
Well, because remember what it's doing. It's going to have fetched the instruction code in T2, right? So your expectation is just like on the SAP1, it's going to halt as soon as it recognizes the instruction. It turns out that it hasn't fully in the instruction register in the controller sequencer done that until it's part of the way through T5. And it's, from our perspective, we really stopped halfway through T2. We don't have anything in our documentation. Remember I told you that the original documentation on this device has some errors? One of the errors is that the halt really does take 2.5 cycles. But the guy that invented the machine forgot that when he wrote out that sheet of paper, and he included all the execution steps mistakenly. So it's actually wrong. But when you do your calculations, use what's on the documentation sheet. Don't use 2. But if we were to build this and we tested it, it would literally stop in the middle of the second T state.
Okay, perfect.
Yep. Okay, so the next 3 numbers are what's in the accumulator, what's in the B register, what's in the C register. Then the next 2 are the sign flag and the 0 flag. So if we do an instruction that sets one of those, they will be turned into a 1. If you look up here on mine, the 0 flag had gotten set and nothing else ever reset it. So it stayed 1 all the way through the rest of the, I don't scan back far enough to be in code that didn't test that, but it was already setting the 0 flag. And 0 flag was right up there, right? Because until that flag came on and made it non-zero, we weren't going to proceed ahead. We'd stay in a tight loop. So this is one way we could do it. Now we wrote another variation of this. Let's go ahead and write that other variation. We can notepad, again, name it after yourself, but call it, number 2. DRB2 for mine. As I recall, and I'm working from memory here, so you've seen my memory. It's not, I'm running with, 1952 memory or something, but we said we'd use a load immediate if we knew what the numbers were. If we know it's a 32, we can load the accumulator with a 32. Remember, on the load immediates, we could use any of the 3 registers. However, on this machine, it's not called load immediate. What is it called? It's called a move immediate. So we can move the 32 to A. We could move to B, the 17. And we could do our add from B. I guess we're adding to the accumulator from B. Then we can output, go to, we can halt. Now, who knows if I got the instructions all right? Oh, and then we really, to be proper, need an end statement. So I can ASM of DRB2.asm, seem to have worked. Then I can do a simulate of DRB2.hex. And it should have run. Over here is my window. Should get the same answer. And if we look at this, we'll see that initially we loaded the 32 to A. We added the 1, or put the 17 in B. We added B to A, which gave us the 49. And of course, output doesn't change any of the 3 registers, but it does takes the 49. We'd expect to see a 49 here, and there's a 4, and there's a 9. So that all worked correctly. Up here, really, the only difference was we were loading the registers. We had to load, then we had to move it to B before we loaded this guy to A again. So we could look at this and study the difference between them, or among them. So any questions on those? Okay, let's write a quick program. I close these old ones up. I don't need that anymore. And just because it's in the way, we'll get rid of that. I need that. I need that. Okay. So let's write one. Let's write one that can turn on a bit based on us wanting to turn it on. This would be good practice for us anyway. I'm going to use tabs because it'll line things up a little more nicely. Let's assume that what I want to do is no matter what number is in the accumulator, I want to make sure that that bit is on at the end of the program. You know, 0 there, don't I? 2 nibbles. So we want the accumulator, no matter what number I start with, to have that turned on at the end. So first step here, we'll load the accumulator with some arbitrary number. We'll output the accumulator when we get here. In between, we need an instruction which will guarantee that that is going to be turned on. Think about your hardware, and you should be able to come up with an answer for that. What would the instruction look like? I had a coughing fit. But as you know, it's not the cough that carries you off, it's the coffin they carry you off in. Okay, what would it be, Dante?
So I haven't fully thought it out, but so far what I'm thinking is we do similar to our key loop program, where we isolate it through the AND to see if that bit's enabled. And
Well,
if
we want to guarantee it's always on. It's a slightly different question here. In that case, we were checking to see if it's on. In this case, we're forcing it on.
Yeah.
So the way you're thinking is a good start, but let's think a little bit more about it. Robert, do you have a possible solution?
Yeah, we're going to OR it because that way if it's a 1, it's good. If it's a 0, we're going to OR in a 1.
So you're suggesting that we would use an OR immediate?
Yes.
The accumulator with what value?
0, 0, 1, 0.
Well, I only have 2 bytes. I have whatever this byte is, or nibble. I have 2 nibbles. Where is this bit located hex-wise?
Hex-wise, it's going to be in the first.
The left bit, right?
Yeah.
And what would its value be? Scott, what would it be?
02.
Well, 02 would be this bit over here. It'd be 02.
It's not little endian?
Well, this is only 1 byte. These are binary digits.
Okay. So it's 20.
Yeah. Okay, so when we run this, we're going to have output. We're guaranteed that in the left 4 lights, this light should be on. So let's test and see if that works. So we do an ASM, brb3.asm. Oh, I have a syntax error. Line 3. What's the syntax error?
You're giving it too many parameters. It's already going to OR A, so we only need to give it OR I.
Well, this
20.
is line 1. This is line 2. This is line 3.
LDA isn't a thing.
You don't
wait,
think?
no, it is.
Okay.
No. LDA 03.
Anybody can jump in there and come up with a solution to this.
Oh, LDA needs 2 bytes.
It needs a
Or-
full 16-bit address. Yes.
Right.
This is an 8-bit number. So either we have to create an address. I'm sorry, this is an 8-bit number. Either we have to create an address, and if we use the address 3, the address 3 is right in the middle of this instruction. So we can't probably use that directly. A better thing to do would be to use a load immediate, which we said is not really load immediate on this machine. It's a move immediate, MVI. And we need to tell it where to move it. Let's save that. See if that fixed our woes. Syntax error, line 4.
Now it's what I was saying before. We have too many parameters for ORI.
And the reason is,
it's expecting 2 bytes and we've given it 3.
yeah, but conceptually, what is it doing?
Oh, it's
What
always
does an OR mean? It's
it's
always
ORing
with
against the
regards to the
accumulator.
accumulator. Now we have no errors. We still don't know if the program does what it's supposed to do. Remember, it's never going to check that for you. So we should be able to simulate it. And we should be able to use drb3.hex, I believe we're using. Now, if we're lucky, the 03 is going to be changed to a 23. Here it is. Now, look at this. We have a bug. This program is looping forever. I don't see any jump statements. And look at those huge addresses. And look, the opcode is all 0. What the heck is going on here? What's going to happen when it gets to FF here? Coming up right now, it's coming up there. It ran some stuff. What do you think's going on right now, Miguel?
Is it because we didn't put the halt statement at the end?
Absolutely. Without a halt, what's it going to do? It's going to keep executing instructions. It turns out, we go back to our data sheet for the instructions. Oops, I got the wrong one. I looked at it and clicked on the wrong one. Wait a minute, I only have the wrong one. No wonder. We look at the data sheet for the thing. We'll see that a 00 is a no operation, a no op. No op means don't do anything. So it's executing thousands and thousands of nothing. And then it rolls around at FFFF back over to zeros, in which case it re-executes our program again. And then lots of no ops. So putting the halt there should help us. Looks like I forgot. I didn't get the compile done correctly. We are using DRB3. What?
You gotta save it.
I didn't save it over here?
No.
Okay. There we go. Okay, so now we executed our 3 instructions. Notice we had an 03 in the accumulator. After the OR, we had a 2-3, and we kept it for the output. Of course, this guy's going to show the same answer because that's what we did. Now, to verify that it's really working, there's 2 tests we have to run. One of the tests is it still going to work if that bit's already on? And in fact, yes, it does. What if this has another bit on with it? And indeed, it's still on. So we seem to have written code that would do that. What if we wanted to have both of those bits turned on? How would we go about doing that? What would we change in our program? Hermel?
Oh, you change the ORI So like the second digit instead of a 0 would be like 8. I think.
So what will it be? The 2 is still there. What's this guy going to be? You saying 8?
Yeah.
So a great way to check would be, let's make this 0. Oops. That's right. And try running it again. And now we of course could look down here and see we have a 2.8 in the output. 2.8 in the output. So if you want to turn a bit on, regardless of what the other ones are, and regardless of what the current state is, this guarantees it'll be on when you're done, no matter what the rest of the bits are doing. The thing we did earlier, which was identify whether it's on or not, is a separate exercise, but it used an AND in order to determine it. And we just talked about isolating a bit using it. What if we wanted to guarantee that a bit was turned off? How can I guarantee that a specific bit is going to be turned off? Again, go back to your hardware, because you learned how to do this using hardware gates. Algorithmically, let's assume that I have some number, let's use 8 of them, of zeros or ones. When I'm done, I want to guarantee that there's a 0 there and a 0 there. The rest of them, I don't care what they are. I want them to be what they used to be. But I want to guarantee those 2 bits are 0. Robert, what do you suggest?
Zor 28.
Do we want to do it with cheaper gates than that?
We could do NAND.
Well, that's kind of where we're headed. But thinking about it kind of in a way, if we see ID the spots, we know that we could isolate those spots that way. All right, that's going to isolate where they are. If we take and we were to use that function with it, that's where we would put the 0 if we could, using your NAND idea. However, we also know that ANDs are only turned on where we have a 1. So if we make our mask look like this, which is the inverse of the positions of the bits we're interested in, and then we do an AND function, we can turn off the bits that we're interested in. Scott?
We can apply the CMA command to get the ones complement of our mask.
Right. If we need to calculate it. If we don't need to calculate it, we can just pre-calculate it. we can just say in advance, but yes, you could. So let's say for now, and we'll do the pre-calculate way, then we'll try out Scott's way here in a second. Let's say that I have a number, and let's do a move immediate into the accumulator of that number. And the number is 67 in hex. Now I know what the mask is going to be in order to do with this an and immediate of the accumulator, of course. And what's going to be the value I need to do in order to turn these two bits off? Well, we would take an OR type of a thing, or a positional mask, and we would invert it. So what is this value right here? Scott?
D.
And what is this one?
7.
So we should be able to use a D7 if we hardwire it. And then we should be able to produce the output from that into that register. Let me actually capitalize the word end here. Don't always do it because it's a directive, but we will for now, and a halt. Now we'll let the machine tell us if we have some errors here. ASM drb5.asm. We'll simulate drb5. That is, it won't work. Bad file type because it should be the hex file. Okay, now let's think about, is it doing what we told it to do? It wound up with a 4-7. So taking the numbers we have, let me just write them down here. We have a 67. We said we wanted to turn off, let's use X's here, that bit and that bit. So if we turn those bits off, that means the 0 and the 1 will pass through here. This guy will be turned off. He'll pass through. This guy will be turned off, and all the rest of them will pass through. The value we'd be hoping to see would be a 4-7. Well, it turns out that is a 4, and that's a 7. We guaranteed those would remain off. We look at our output just to verify it. It should match our trace, actually. Yeah, 47, 47. Now let's assume, just for the heck of it, let me keep that file for now. And I'm going to copy it, lock, stock. Well, actually, no, we'll write it from scratch since you guys are not catching on as fast as you should be. What are we up to, 6? Okay. So Scott, I'm going to put in the register here the number that represents the bits we had in the last thing, which is a 2-8. Ultimately, before the halt down here, we want to output the answer. So now you had an interesting thing to do to our 2.8 here. How are we going to take care of turning it into a proper mask?
Well, before we get started, do we need to do MVIA and not load A?
Oh yeah. You can tell what your next processor is going to be using. So how do we turn that into a mask?
All right, so if we invoke CMA, that's going to give us our desired mask.
Okay, we don't need to specify any parameters, but basically what it's saying we're going to do is we're going to take a 2, let's leave that in the comment, 2, 8, and it's going to complement it into 11010111, which is the proper mask. Now that's in the accumulator, however. So we're going to now pick up the number, but we want to save it first. How do we get it somewhere where we can save it? I want to put it in the B register. How do I do that? Scott?
We can do MVI B and then whatever our number is.
Okay, well, we'll actually use a move because we have it in a register already. Right? We want to move it to the B register from the A register.
Oh, okay.
Now we're going to do the MVI to the accumulator of the number we're actually dealing with. What did we say last time? 67 or something? I don't remember. And then we should be able to actually do our AND. What number did we want to use here? Well, we can't use it from memory, so it can't be a regular ANI. It has to be an AND instruction. It's going to happen to the accumulator from where? Scott?
It'll be from B, so we want to use ANA B.
Is it an ANA on this machine instead of an ANA, AND?
Yeah.
Okay. And then we have an output instruction. So if we did everything right, we should be able to do a assembly of number 6 over here. Add file type. I didn't do 6, did I? Then we can simulate 6. And again, we got our 47, which was the correct answer. So this is a good way. This is an interesting way. It takes more T states, but what flexibility does this allow that we didn't have in the other program? There's a tremendous flexibility gain here. What did we gain by doing it this way that we don't have over here? Scott, what do you think?
Well, we can do a lot more with the mask here. We don't have to figure out from scratch what we want to do every time if we want to get different patterns.
Right. In this program right here, we're assuming that we knew this number when we compiled or assembled the program. Over here we are too, but chances are pretty good we wouldn't really have this instruction. What we'd have here is maybe getting it from the keypad. So by putting this in memory somewhere rather than doing an MVI to get it, that gives us the flexibility of changing the mask. We don't even have to know what the mask is internally. We just have to know what bits we want to have to turn off. So this is a little less flexible but faster. This takes a while longer, but adds us that flexibility. And we'll see when we need that, when that comes in important. Remember, all these processors we're working on are leading to one that's going to be used on the mega chip in a couple of weeks. So make sure you're not missing any of this. I may not come back and cover the material again, but those machines do the same things. Okay, you'll even see me pulling instructions out from other machines, and hopefully you catch me, or the assembler catches me when I type them wrong. Okay. Okay, let me write some code here for us. Okay. I want to output right here the average of those four numbers. So think about it for a second. Jot down on a piece of paper how you'd go about calculating the average. Okay, anybody want to share with me your strategy? Nobody? Scott, what's your plan here?
Well, I've got something I'd like to do, but I'm puzzling how to do the division part, right? I mean,
Okay.
at a high level, you want to read in the data, accumulate it, also count the number of data points, and then somehow divide that cumulative number by the number of data points.
Okay. Well, we know in advance there's 4 data points. We actually have in our memory the data we're going to use. So we won't have to get it from the input. We could, but in this case, we'll assume we have it in those 4 data bytes, and we know that already in advance there's 4 bytes to be dealt with. if that helps. Let's take up the part of accumulating it. How am I going to go about adding those guys together? Robert, give me a strategy for doing that.
So you would use LDA to take the data at address 8000 into the accumulator.
Let's do that.
Then
Load the accumulator from address 8000.
Then I move that into B, so move BA. And then we're gonna add it. So add B. And then we're gonna move it back into B from the
Well,
accumulator.
didn't we miss one thing there? We never got the data at 8001.
Oh, yep. I'm sorry. You're correct.
Oh.
And then, yeah, so then we would add it and move the result into B and load the accumulator again.
You're going to move your result, which is going to be from A. Okay.
Correct.
And then we're loading the accumulator again.
With 8002. And rinse and repeat.
We're doing what?
We're going to do the same add B,
Tell me what to
move
do.
BA. So add B, then move BA, and finally load the accumulator from 8003 and add B. And at that point, we would have the running total of the sum of the four.
Well, we can
digits.
check that. Let's actually compile and see if that works. What's this? This is number 7. And we should be able to simulate that. And the answer we have is a D3. So, is that what this adds up to? No, not D3. It's a next column over, 5-2. Somebody want to add that up in hex? Is that right, Scott? Okay, thank you. Okay, so we got the right answer. Now what do we need to do? We have one goal left, which is to find the average. Scott, what do you think?
So we're allowed to use the fact that we've got 4 data points. We don't have to calculate 4, right?
That's right. We know that we have 4. I gotta go find my data. I've lost my data sheet. Oh, maybe I didn't. Is that it? Oh, it's on the other window. That's why I can't find it. Okay. I just wanted to make sure we had that. Okay, so what's the plan of attack?
So one thing we could do is kind of set up like a loop where we subtract 4 from this cumulated total until we get to 0 or negative in the accumulator.
Mm-hmm.
And all the while we need to count the number of times we're looping.
Okay, that's a way to do it. There's actually a simpler, well, I won't say simpler. Once you get it, it's simpler way to do it on this machine. Do you remember one of the things about our machine here? We have an ALU in it, and this ALU can do logic instructions, and it can do math. And it also had a couple other funny, like to complement the accumulator, but there were a couple other little things it could do, which were pretty handy little gadgets to be able to do. Remember these guys? Rotate the accumulator left and rotate the accumulator right. If I take a number, go back to my hardware days here. Let's say the number 2. And I rotate it 1 position to the left. Well, the high order bit's going to come into this end, but the net effect is the 1 is going to look like it moves 1 position to the right. I'm sorry, to the left. This was the number 2. This was the number 4. If I move it again, become the number 8. You see this powers of 2 thing going on here? What if I were to move, what if I started with this and moved it to the right? We did a rotate right. Well, yeah, this bit would come in the other end. We'll have to deal with that. But I would basically be dividing by 2. So if I did that twice, if I took 8 and moved it over 2 positions, I'd have a 2, which is 8 divided by 4. So how about we do that with the value that's in our register right now? It's in the accumulator. We want to divide, so we basically, I'm going to keep this little separate code here for this. Where'd my thing go? We rotated the accumulator to the right once. And then we rotated it to the right 1 more time. And we have effectively divided it by 4. Forget about the extra bits that might be coming in the wrong end. We'll fix them in a second. So let's run that. And see what we get out of that. So what was the number we had a few minutes ago that we added up? Was a 5, 2? And the number we're getting now is a 9, 4. Well, let's think about it a second. Let's write down our 5, 2 that we're trying to divide. Five, 2. Let's rotate it 1 position to the right. Let's rotate it a 2nd position to the right. Notice the 1 on the end there is going to come in here. It is a 9, 4. It's a 9, 4. The problem we have is that if we didn't have this 1 that came in here, all would be well with the world, because we would have now the number 1, 4. And 1, 4 sounds like it's approximately a fourth of that. We'll check it in a second here. But what we need to do is, after the rotate, we have to make sure that that high bit is a 0. So what instruction did we use to cause the high bit to be cleared? We ANDed it with something, didn't we? With a mask. We did an AND immediate. What would the mask be if it wants to touch only the top left bit? What number could we find there? We want to clear that leftmost bit. Dante?
The 8, 0.
8, 0, that's exactly right. And we'd have to do it on both the rotates. We just turned our rotate into a shift instruction. Now let's take a look. Run. Now we look like we wiped out the whole number. What did we not do with the 8, 0? Scott?
We need to turn it into a mask to turn off the bit, not turn it on.
Right. So that would be a 7F. See why knowing these things is handy? It's great you came right up with that answer that quick. Assemble, simulate. Now we have 1, 4. If we were to grab our calculator and we threw it into programmer mode, I think it's this button. Is that button? No, that's the one that locks it on the screen. Where's my modes? Are they over here? Oh, here they are. We took a 1. Oh, we're in decimal now. Hex. 1, 4 times 4 equals a 5, 0. Okay, we're pretty close. Can we explain away why it doesn't come exactly back to the value? Why was this times 4 not equal to the number we're taking the average of? Dante, what do you think?
Because the average like this, some amount of decimals.
It has a fraction part. We actually saw the fraction part. Know what it was? It was that number that went around and came in the front end of the rotate register. So if we assume that our average is going to be mod 8, or mod 4, I mean, whatever the value, mod 8 here, I guess, is going to be, then we can take and say, well, half of the value could have been lost because it's a fraction, or a quarter of the value, to get the mod 8 type of stuff going here. So what we need to do is, did I close that calculator again? I think I did. I go back to just plain old standard mode. What did we make our number? We added all this stuff up. What was this? What was the hex value of this? Does anybody remember? I've lost my window here.
It's 5, 2.
It was a 5, 2. 5, 2 is not a power of 2. Is it a power of 2 plus 8? Is it a power of 2 plus 4? Or some multiple of 4, like 12, that sort of thing. Well, the problem here is we don't have any place to put the fraction. We know how to do it, though. Anybody want to remember back to the very first night of class on how you can handle fractions when you only have an integer format? Even had a question about it on the exam. Well, the answer is when we store the number 4 there, that first number, we're leaving no room for the fractions. If we assume there's a decimal point in this number and we move this over 1, then later when we read our answer, we can insert a decimal point right there. We have less digits in front of it. If we wanted to see if it was going to leave, either half or a quarter or 3/4, we'd move it one more position over, which would leave us 2 positions for the fraction. I think I deleted an extra 0 there. No, I didn't. So this would still be a 4, but it's in that part of the number. And it has 2 fractions, one for halves, one for quarters or 3/4. If all of them were lit up. So if we wanted to do that, after we loaded these values into the register each time, we would need to move them over. So for example, we have all 4 moves as moves. The last one's actually not a move, is it? If after we load the accumulator each time, we did a rotate left, or rotate all left, we'd have to do 2 of them in case we have 3/4. I haven't done the division here. We might need 16s. I don't remember. Once we did that, we'd have to do a mask. Mask off now, in this case, the fact that if we rotate to the left, we're bringing in data that was on the left into the right-hand side. For the numbers we have, that might not be dangerous, but we have to clear out those 2 bits that we just brought in. So to do that, we would end with the inverse of a mask, which the mask would be 0, 3. So what is the inverse of that mask? How about F Charlie? Then we would do these same instructions again every time we loaded a number in. Hopefully I put those all in the right spot. Now that gave us a 1, 2. That doesn't sound right, so I probably have typed something wrong over here. But if we take 1, 2 and we were to give that a value, let's see what we have. We have 1, 2, we would have taken this number right here. Here's our 1. And the 2 bit is this guy right here. So this number is still a 4, but this guy indicates 1/2 in fixed point binary. We're pushing on time. We've got to move ahead, but I want you to think about that. The representation of the number could be in binary, or you can change it to fixed point. Did I type the right numbers? I don't know. you can fix that and check it yourself with the calculator. But the idea there is that where we encode the number matters. What we did is when we made room for these 2 digits, we had brought in the 2 digits on the left. If these numbers had had 1s in them before we did the rotate, these would have had 1s that we had to get rid of. So the result then could replace those values with zeros. We need them to be zeros. Okay, I'm going to move ahead. That's one you want to just kind of work through. And like I say, I probably didn't type everything right because the 1, 2 here sounds suspect. We could see what it is. For a 1, 2, that means the decimal point is the last 2 positions, which is a half, which would be 4.5 as far as an average number. I don't think that makes any sense with these numbers. No, it's got to be bigger than that. So I made an arithmetic mistake somewhere, but you guys can go through and figure it out. I'll let you do that rather than spending time now doing it. Okay, everybody remembers that. Let me just review with you very quickly that you do remember fixed point numbers. If we wanted to represent the number 4.5, how do we write that down? Well, we write the number 4, the decimal place, and we write the half, which is here, but we move it out like this. So in our case here, if we wanted to reserve room for this, we'd have to push this number to the left so we had at least 1 more decimal point to contain that value in. If we needed quarters, we'd have to push it 2 positions. 8ths, we'd have to push it 3. 16ths, we'd have to push it 4, and so forth, which gives us less and less room to store this part of the number. Okay, let us move ahead. Let's assume for a second that I want to use the keypad and I want to add up 2 numbers that I type in. So if I type a 4 and then I type a 5, I want to get the number 9. So let's think about the code we need. We have some code we can steal from to begin this one with. So what I'm going to do is I'm going to copy DRB it was SAP 2.asm to DRB 8.asm. And then we can notepad DRB 8.asm. Okay. I am going to call this key loop 1 because we're going to be getting 2 keys. Now, at the point we get to this right here, we have our first key. The first key at this point is in the accumulator, and we display it. We don't want to display it. Let's instead move it to the B register. Now we need to repeat this code. Call this loop 2. In this case, we don't want to move it to the B register. We want to add B to A. Now the answer should be in the accumulator at that point. So we should be able to output what's in the accumulator. And then go back and get the next pair. Let's instead halt so we can see if it works or not. And eventually we can jump back to key loop 1, which would be the first key again. But for now, we'll just put this in here to test out what's happening. Let's save it. ASM DRB 8.asm. Oops, so something on line 6. 1, 2, 3, 4, 5, 6. Got to say where we want it to go. From the accumulator to the B register. Okay. Let's add a 4 and a 6. That doesn't look like a right answer to me. So what is the answer really telling us here? We added a 4 and a 6 together. We'd expect to get a 10. A 10 will be an 8 and a 2.
We've got a spurious move I in there.
I think so. Where did I put it? Which one?
Right below where the cursor is.
Well, you all are in more luck than I am if you can see my cursor. Where this is? This guy?
Sorry, yeah, that one, and there's an analog above it.
Well, we need those, right? The trouble is, we're printing the answer after we acknowledged the character. And since we did that, we've changed the accumulator. So we could save it in C and then move it back, or we could just move where we do the printout. See if that's a better choice. What did I have last time? A 4 and an 8? 4 and a 6? Got an 8 and a 2. That sounds like the right answer. And it halted. Okay, we should be able to get rid of the halt and let it run. Yep. Hey, let's try some simple ones. 0 plus 1 equals 1. 0, get locked. Aha. Interesting. Why did it lock? Easy answer to this one. What is it, Robert?
Oh, it hit the halt.
Yeah, I forgot to get rid of the halt. I got rid of the blank spaces. If you got so intent on that, I never got rid of the halt. Okay, that's over on this screen this time. So we added a 0 and a 1, got a 1, 0 and an F, and got an F. Let's try 2 plus 2. Got a 4. 10 plus 10. Got a 16 and a 4, that's a 20. Notice we've got 5 bits in play right now. F plus F will be the biggest number we can get. 15 plus 15 should be a 30, and it is. It's all the bits turned on except for the 1 bit. So it's not 32, it's not 31, it has to be a 30 that's there. This is still running, so we're still looking for characters. 8 plus 4, 12, that's working. So now we have the ability to enter characters, save them, and pay attention to them. Anybody have any questions about this particular piece of code we just wrote? Okay. It was 8. Actually, I didn't want to copy that. Doesn't matter. I'm going to get rid of all this anyway. Okay, what we want to do is we want to solve a problem which is given to us kind of as a high-level notion. And a compiler writer might encounter this. We want to do something like, if variable number 1 is equal to variable number 2, then do the true block, otherwise do the false block. So we'll pretend like we're going to generate some code which would always begin start if. Let me indent this with a tab. And let's assume in working our problem, we have some data elements that have been generated for us. We've got a byte, which is equal to, we'll make it a 13 for now. This guy is actually variable 1. I'm going to put a 12 there. This is variable 2. We've determined that through some mechanism in our compiler writing. So what we want to do is we want to analyze this statement and do different code. Now, this block could be gotten from somewhere else and just inserted into our code. But we want to have the notion of a true block and a false block. So let's set this up to test to see if something is equal. What I'm going to do is load the accumulator from 8001. I'm basically getting here variable 2. I'm going to move that to B. And I'm going to load the accumulator from 8000, which is variable 1 again. Now I need to somehow figure out if they're equal. Anybody have any suggestions for how I might do that? Anybody other than Robert and Scott going to put their hand up? So what do you think, Robert?
I don't know exactly how you would implement it, but you could take the 2's complement of the variable 2 and add it to variable 1, and if it gives you 0, they're equal.
Okay. When you take the 2's complement of a number and add it to the other number, what is that operation called? We did it on the SAP1.
While subtracting.
Okay, I like that. Or we could subtract. It's going to be from A, right? We're going to subtract B from A. Now, what did that buy us by doing that?
That's going to give us a value in the accumulator, which if that value is a 0, then they're equal.
Well, how would we know it's a 0?
Well, it would with sub. It's going to give us a 0 flag.
Okay, the Z flag will be set, the 0 flag. So that means that we can test the 0 flag. Scott, how can I test the 0 flag? I want to do something conditionally based on whether the 0 flag is set or not. Do we have any instructions that do that?
Oh, sorry, I thought my mic was on. The JZ instruction will test if the 0 flag's on.
Hey, JZ, so we're going to jump somewhere. So if it is 0, we'll jump to the true block. If it's not, we'll fall through. And as good compiler writers, even though we'll probably remove it later, we're going to unconditionally jump to the false block, which is right here. Notice how we're going to later on be able to optimize that jump away. And all we're going to do for this is we're going to move to the A register 0, and we're going to output it. So if 0 show up, that meant we had a false condition. Then we're going to jump unconditionally. Again, we may optimize this away to the if is done section. And if is done will be down here somewhere. And if done has very little to do, as you might imagine. It's basically going to be where our halt lives. So since we have to jump over something, the thing we'd probably be jumping over here is the true block. For our true, we'll just do a move immediate to the accumulator of FF. I'll output that. If we ever get all ones on our display, that means we had a true statement. And when we're done with this, we can jump to if done. And it might be the very next instruction, but we can get rid of that in the optimizer. We won't do it here while we're writing code. Now, should that work? Is that going to test for equal? I'll push this down a line just because it's prettier that way. Give me a green circle if you think that's going to work. Okay, so ASM drb9.asm sim drb9.hex. We don't have to look even at the lights. We have 0, 0. That means they're not equal. They're not equal. Let's make the bottom one bigger than the top one. Let's run it again. They're not equal. Make them have the same value. Oops, hang on a second here. Forgot to assemble it. There we go. What did I just do? Oh, I assembled it twice. There we go. And if we look over here, just like Macy's, it's all lit up. So they are equal. Now, as compiler writers would be generating assembly language, this is how we would generate an if statement, perhaps. What if we wanted to test for not equal? What has to change in our, let's call this a template right now. What has to change for us to change this instead of being equal to being not equal? I know you guys are thinking he can't flunk all of us, but he has flunked them all before. So don't just try not to participate thinking I'm not noticing it. I've got two hands that have been coming up all evening. And unless the rest of you are just not there, but green circles gave you away, you're not participating. Yazoo?
So we're gonna change the like under the line J to like JNJ and JMP to like JNJ.
Okay, so I can make this an N.
Mm-hmm.
I'll test for not 0, meaning
Right.
not equal.
Right.
Okay, now if they are equal, this is still going to the right place, right?
If they
So
are
I should be able to pretty much handle that guy. Let's prove to ourselves that that might be the case. Right now they're equal. So if I assemble it and I run it, I should get back a 0, meaning they're not equal. If I make them different in any way, assemble it, simulate it, or they're different, you'll get blue lights. What if they're the other way around? What if we make the second one be bigger? They're different. Okay. So you can only imagine that this isn't a very challenging problem to change them to something else. Let's say we wanted, instead of not equal, we wanted to do greater or equal. Think about what has to change. Now think it through. This is a little different than you might expect. Because if you look at the instruction sheets, we don't have all the instructions you might need to make this be done in the fashion it's been written so far. Okay, what we want to do is we would want to say, is it greater? If so, pass it, and then check, is it equal, and pass it. The problem is, to test for greater, we'd have to test to see that it's a positive number. We don't have an instruction that does that. We could build one out of ands and things, but we got one that does the opposite. We have the ability to check to see whether or not a number is minus. Now, if it is minus, we don't want it. Matter of fact, that's the only thing we don't want. Right? Well, not quite true. We want greater, yeah, but equal is going to be taken care of if we throw away the minuses. So how could I make this throw away the minuses? What could I do to that line to make it throw them away? Scott?
Change the parameter to F block.
Okay, and if he goes to F block, what's the next guy have to go to?
T block.
Exactly. So it's not very tough to be able to do these type of problems. You should be able to think your way through something like this should it appear somewhere where you need to do, for instance, somebody said do less than or equal. Would that be more challenging? Because you have a test that will let it pass if it's less, and you have a test that will pass if it's equal. Maybe that becomes really easy. Let's actually do that one. What do we have to change? Mazu?
Is it, I'm not quite sure, but is it possible to change the LDA 8001 to like 800 and the other one to the other variable?
No, not for this problem. Dante, what do you think?
Do we? Because I know if we switch the block sort back around, so the JM, it's JNT block and JMP F block, it'll jump over if it's a minus. I'm not 100% sure if that'll work for equal.
Okay. Well, one of the things we could do is we could always test for the equal case first, right? We could just say if it's JZ, it's good. So where do we go if it's good? Go to T block. Now we can check for minus. If it's minus, where do we go? It's good. We go to the T block. Otherwise, it's not any good. So we can jump or fall through, but we'd probably write this and then in the optimizer get rid of it later. So I'm not going to run that because we need to get wrapped up here pretty quick for the evening. Make sure you're studying this stuff. Don't come assuming you're going to take some notes. You've got to get it into your heads because as we go to more complicated assemblers, this stuff all carries through and the instruction names change. You've seen me even spelling them differently here. You're going to have to remember which is which for a particular machine. You always have the data sheet, but if you spend all your time there, it's going to be like trying to figure out hex numbers by looking them up. You'll just be too slow. Okay, homework. You do have some homework. It's going to be writing a program using the SAP too. I want you to write a program which, given a string of bits, So let's say you get in, 8 bits, and it will always be 8 bits. I want you to display them on the lights in reverse order. So assuming you get past this N, which is what is that in hex? It's a B7. I want you to display an ED for the output. You got this number. You're going to display that number. Always the inverse in terms of bit, not the inverse in number wise, but in terms of the ordering. You're just going to change, put them in the opposite order. Now, where do you get the data from? Your choice. You can get it from pushing a key on the keyboard, in which case you display only the backwards number, you don't display the forward number. Or you can put it in a data section down here and change it every time you run it. I would suggest the keyboard for maximum points, but on the other hand, if you get this one working and you can't get the keyboard one working, this was a better choice. So the ideal one will come having you type a key and that key be displayed in the lights backwards and then go back and ask for another key, right? It'll be an endlessly running program. An acceptable one will be a program like this that has one pass through and hits a halt, where you give it the number either in a data area or in something that can be loaded with a move immediate, and you can change that number and the right answer comes out. You can work with other people on this, except you can't share code. So you can't sit down and copy code from somebody else, but you can talk about it with anybody else in the class except me. Any questions about the homework assignment? You're going to mail it to me, but you're going to wait to mail it to me until class starts. I'm going to have some of you demonstrate your programs at the beginning of class, next class. Okay, any questions about that? This is your chance. Okay, then we're done for tonight. Make sure you study this stuff and get that homework done. And like I said, you're going to email it to me, but not until class begins next Monday. Bye-bye.
Good night, Professor.
Good night.